The year Einstein broke reality. In 1905, a 26-year-old patent clerk broke the universe. Not from a laboratory, not from a university, but from a small office in Bern, Switzerland, where his job was to approve other people's inventions. His name was Albert Einstein, and in a single year, he published ideas so radical that physics has never been the same. This year is now called Einstein's Annus Mirabilis, his miracle year. In 1905 alone, Einstein published 4 papers, each attacking a different foundation of reality. One showed that light behaves like particles. Another proved that atoms actually exist. A third rewrote space and time themselves. And the fourth produced a short equation you've seen everywhere. E equals mc squared, revealing that mass and energy are secretly the same thing. Here's the part that sounds impossible. Einstein didn't use insanely advanced math, no abstract machinery, no new mathematical tools. The equations were mostly algebra and standard calculus math that university students could follow. And yet professional physicists were completely confused. Not because the math was hard, but because the ideas were unbearable. Before Einstein, time was absolute. A universal clock ticking the same for everyone, everywhere. Einstein shattered that assumption. Time depends on motion. Space depends on motion. Even simultaneity depends on who's observing. 2 people can disagree about whether events happened at the same time and both be right. And somehow, despite all of this, the speed of light stays exactly the same for everyone. Accepting this meant abandoning common sense, not learning new equations. That's why relativity felt so disturbing. But even Einstein knew this wasn't the end of the story. Special relativity couldn't explain gravity. Starting around 1907, he began chasing a deeper theory, one that could handle acceleration, mass, and gravity itself. And for years, he failed. His notebooks from this period are filled with crossed-out equations, wrong ideas, and abandoned paths. He had the physical intuition. He just couldn't express it correctly. The breakthrough didn't come from physics. It came from mathematics that already existed, but almost no physicists were using. Decades earlier, mathematicians Gregorio Ricci-Curbastro and Tullio Levi-Civita had developed a powerful framework now called tensor calculus. It was designed to describe curved spaces, not gravity. To most physicists, it was obscure, abstract, and unnecessary. But it turned out to be exactly the language Einstein needed. In 1912, Einstein did something crucial. He asked for help. He turned to his old classmate Marcel Grossmann, now a professor of mathematics. Grossmann introduced him to Riemannian geometry and the tensor methods of Ricci and Levi-Civita. Suddenly, Einstein could finally write down what he had been trying to say for years. In November 1915, everything snapped into place. Einstein presented the final equations of general relativity. Gravity was no longer a force pulling objects together. It was the curvature of space-time itself. Matter bends space-time, and space-time tells matter how to move. The equations were beautiful and brutal. At the time, only a small number of experts in the world could fully follow them. Then came the tests. The theory explained a long-standing mystery in Mercury's orbit that Newton's laws couldn't solve. It predicted that light would bend as it passed near massive objects. And in 1919, during a total solar eclipse, that prediction was confirmed. The measurements matched Einstein's theory, and the news exploded across the world. Overnight, a former patent clerk became a global symbol of genius. But Einstein's story isn't just about intelligence. It's about something deeper. Scientific revolutions don't happen because someone is smart enough. They happen when new ideas meet the right language. Quantum mechanics needed new mathematical tools. Chaos theory needed computers. And today, our search for a theory of quantum gravity may still be waiting for its own breakthrough language. So here's the unsettling question to leave you with. What truths about our universe are we still blind to, not because they're false, but because we haven't yet learned the right language to describe them?
Thanks for watching. Join our community of forever curious minds by liking, subscribing, and turning on notifications so you never miss a video. Until next time, stay curious.